Nicholas Gates, and my TID is 00147-689 for Grantham University ET450, and it's my capstone project for temperature monitoring system. This is my mock-up and model of my temperature monitoring system for my capstone project. All of my testing pictures and videos will be part of my slideshow presentation. The problem we had was for my project was there is a cabinet in a motor control center that is getting excessively too hot. It's difficult to monitor because personnel cannot be in the room with the cabinet for extended periods of time. The choice was to make a hardwire monitoring system to remotely monitor this system from other rooms via a hardware system. So we will have a temperature display, audible alarm, LED indicator, a fan to turn on the keep the cool cabinet, and a sensor to monitor the temperature. We'll have 4 different levels. We have a normal temperature zone, a temperature zone where it's not an alarm or warning state, but the fan starts to cool the cabinet. Have a warning state. This will turn the LED orange and will cause the audible alarm to chirp to say we're in a warning state. And then the 4th zone is a over temperature, which the LED will turn red and the alarm will begin to warble. The fan will be on after the initial first state of the initial cooling state. This is my initial conceptual design, showing the temperature alarm, the audible temperature sensor, the indicator, audible alarm, and an adjustment for the display of the temperature for the panel alarm, and a fan. I also used a relay instead of directly hardwiring the fan. So if need be, the fan can be upscaled to a higher voltage or higher current drawing fan to cool the cabinet faster and more efficient. My first revision was to include a amplification circuit to amplify the speaker off the Arduino. My final design, this will due to a lessons learned, I will describe later in the presentation, was to change my LCD display to use an I2C interface chip to power the display. This allowed to eliminate wiring all the points to the Arduino, thus saving interface space to add more I/O points later. Also, this eliminated the use of the pot as is integrated on the I2C integration chip. This is my initial testing photos from initial testing. This is the first state, normal state, where it's below temperature. The fan will be off in this state, and the LED will be green. This is either photos, all from my initial testing. This is from the warning state. It is now into a warning. The speaker should be chirping. The LED is orange, and the panel display is 91. This is the alarm state. We're over 95 degrees Fahrenheit, so we're red LED. The speaker should be warbling to in an alarm state to alert the operators and maintenance that this is in a over temperature state. Now we'll go on to videos of testing with the mock-up. No, after. No. This is where it came back This is a photo from testing where it came back to normalized temperature before we shut it in testing. Now on the videos. This is the first initial test. This will show where we are at normal temperature, the fan is not on, and the speaker is off. Alright, this is the test mock-up of my test cabinet. The relay's inside and the temperature sensor is inside. I will be doing the blow dryer heat source off camera. Initially plug it in, it should be around room temperature. Alright, it is. Next video will be heated up. All blow dryer tests were all free. Alright, this is the test mock-up. We are at the first step where it's 88 degrees. It's still green, we're not in alarm state, but we have energized the fan. See, it's energized right there, I'm blowing. We are in warning status, 92 degrees. The LED is orange. We hear a chirping sound speaker. And the fan is still blowing. Alright, I got it above. We are in alarm state. We have our warble. And the fan is still running. Alright. So some of the lessons learned during this was ensuring you have a clean soldering tip and using proper soldering techniques. I damaged my original display and had to rush order a secondary display with this time using an integrated chip. This will help with ease of errors in the future and to mass produce if needed to mass produce this system. Also, it allowed more I/O points to be used on the Arduino for future use. Conclusion design was a success. It worked as intended. Everything was under budget and everything completed at time and at cost. So, thank you for watching my presentation of my temperature monitoring system.